Let us begin with a word of prayer. So I will start. Heavenly Father, we thank you for this day. I thank you for these students, Lord. I just ask that you'd bless this class today, Lord. In your name I pray. Amen. Okay, so let's just get straight into it. I'll try to send you an announcement later with some guidance about what you should be reading, to accompany what I'm talking about. Certainly the textbook, the PDF that I posted from Salas and Hilly is useful, but there are also things in my notes which are useful, so I should talk about both. But what I'm going to try to do today is just try to put as many of the cards on the table as I can, so to speak. And so here goes. Power series. So here's the definition. A power series centered at x naught with coefficients C0, C1, C2, and so forth and so on, has the form sum n equals 0 to infinity of C sub n x minus x naught to the power n. So this is what a power series is. In particular, of course, that means C0 plus C1 times x minus x naught plus C2 times x minus x naught squared, and so forth and so on. All right? So if I ask you to define power series centered at x naught, the answer is this. Now x sub 0 and also the c's, these are all what? I'm assuming I haven't written it down yet on the board, but I should probably tell you. In this class, we assume x naught and c sub n are real numbers. All right. Let me just scratch that. Now, you might wonder, do you have to do that? I mean, could you have x naught as a complex number? Could you have C0 or complex numbers? Would there be such a thing as a complex power series? Yeah, you could also do that, but not in this course so much. All right? So this is a power series. So another way to look at this would be what? Another interpretation, we could say a power series is a function whose formula is given pointwise by a numerical series. And you say, well, what's a numerical series? A numerical series is what we've been studying up to this point. All right? So then, if you have a function, what can you ask? What's an interesting question to ask about a function? Let me just be more specific. You might, what I'm saying here might not, maybe this doesn't make sense to you, what I've just written. Let me clarify it, or try to anyway. So let's look at f of x equals to 1 plus x squared plus x cubed plus dot, 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 dot. This is a power series, right? My claim is that this is a function whose value is given pointwise by a numerical series. What do I mean by that? Well, let's try plugging in some values. What would f of 0 be? 1 plus 0 squared plus 0 cubed plus dot, 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 dot. What is that? That series? This is a series that we don't need a bunch of sophistication for, right? You can now all tell me what this works out to. What is it? 1, right? And how about f of a half? What's this work out to? Yeah? 2? And the reason you know that is because you said that that's 1 over 1 minus a half, right? Which is otherwise known as 1 over a half, also known as 2. You identified that this is a geometric series, right? With a equals to 1 and r is equal to a half. So it converges to a over 1 minus r, which in this case works out to 2. So what I've written on the board so far shows you that 0 and a half are in the domain of this power function, power series rather. All right? Let's keep exploring. What happens if I try to plug in? So I'll be a little bit more cagey in my language here. Does f of 1 make sense in this example? Well, what's f of 1? It's 1 plus 1 plus 1 plus 1. If you recall, the first non-trivial series that I studied with you guys was this one. We worked out that the nth partial sum of this series is given by n itself, which of course goes to infinity, which is to say that this series does not converge. This diverges, right? Is the output a real number? Definitely not, right? I mean, if anything, the output's infinity. We don't think of infinity as a number in here, so this is definitely not an allowed output. It's not a real number. So what does that tell me? 1 is not an element of the domain of this function. Right? So my question to you is, what is the domain of this function, this power series? Can you tell me? I'll write that question on the board. We can actually answer this question with another result that we've already proved, right? So, I mean, I kind of already gave it away with the half. Right? What is f of x equal to? In this case, 1 plus x squared plus da 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 da. It's a geometric series. And we know that this converges when? This converges to 1 over 1 minus x. If and only if what? The absolute value of x is less than 1. So what's the domain? It follows, unwrapping this is minus 1 less than x less than 1, right? So in this case, the domain of f of x by the geometric series result is just minus 1 to 1. By the way, the series is only equal to 1 over 1 minus x for these x, right, the function 1 over 1 minus x makes sense for many x beyond the domain of the power series, right? If you study the rational function y equals 1 or 1 minus x, what's it look like? Y equals 1 over, it would be minus 1 over x minus 1, right? Bad choice of, let me make this the vertical asymptote. Hey, I'll put the axis over here. What's the graph of this thing? It's positive. When we go through 0, its y-intercept is 1 as it happens. So we're like that, right? And then down here, one of these deals. So the equality of the power series and the function graph is only true where? I'll do it in green. It's only legit for pretty much here. This, you know, just between, like that, right? That's the domain of the power series. That's where this power series represents the rational function 1 over 1 minus x. Not outside that context. Let me just give you a roadmap where we're going. I'm going to spend a few more minutes talking about the domain of power series, right? We need to come to terms with this because it's kind of the picky theoretical part of what we're doing, right? So I'm going to try to give you an informed discussion about the domain of power series. It turns out there's really not much that can happen, all right? Once we're done with that, then we'll turn to the question of how do you calculate with power series? And then the answer there is shockingly simple. You calculate with power series just like polynomials. Once we're done with that, then we turn to the question of how do you take a given function and find the power series which represents it, right? So that's sort of an overlay of where we're going, all right? Let's continue by example, though. So first, any questions about the first example? Example 2, we could look at f of x equal to the sum n equals 0 to infinity of n factorial x to the n. All right, so this would be what? This is like 1 plus x plus 2x squared plus 6x cubed plus 24x to the 4th plus 120x to the 5th plus, what's the next one? 720 x to the 6th plus 5040 x to the 7th plus, okay, that's as far as I go without thinking. The coefficients are factorials, right? So identify Cn equals to n factorial, right? And what's the center? What is it? 0, right? So, hey, I'll do the easy one. What's f of 0? F of 0 equals 1. And then, what about anything else? Let's try this. Let x not be equal to 0, and notice that the coefficient of the series is what? A sub n is n factorial times x to the n, right? So what I'm saying is fix x. Instead of let, maybe I should use the word fix x. That tells the reader we're like fixing x. It's a particular x. We're going to, in our mind, think about a particular x, all right? But a non-zero one. If we do that, then we're looking at the series where the nth term is what? It's n factorial times x to the n. Right? And so if we look at the absolute value of an plus 1 over an, what do we get? Side note, the ratio test extends to non-negative. The ratio test extends to non-zero series if we just wrap the coefficients of the series, if we wrap the terms in the series by absolute value. So like the theorem, the full ratio test is that a given series converges absolutely. Well, yeah, I mean, there's a, oh, fine. Yes, this is where I was trying to, I'm going to have to cheat a little bit here. Let me just tell you that this theorem applies. Fine, I'll explain. We're going to learn, and I'm not sure I'm actually going to prove this, but it is in fact true, if a power series converges, right, the inside of its domain, all right, away from the endpoints of its domain, the convergence is absolute. This can be shown, all right? So if I can check for absolute convergence, that shows me points in the interior of the domain of the power series. The things I just said, I'm not sure I can really prove them in here. I got to think about whether or not I should prove them for you guys. But checking the absolute value, checking for absolute convergence will reveal the interior of the domain of the power series. Let me just write that down. Checking absolute convergence will reveal the interior of the domain of a power series. What does interior mean? What do I mean interior? This just means like if the domain has endpoints, all right, then we're not going to be able to pick up on those by this test. The endpoints for the domain have to be dealt with separately. Okay? I'll just say that. So if the ratio test works, wherever it works, that is the place that's going to be in the interior of the domain of the power series. The question, though, is, does the ratio test work anywhere? Right? Let's try. What do we got? What's an plus 1? N plus 1 factorial times what? X to the n plus 1 divided by n factorial times x to the n. What's this give us? Oh, absolute value, right? So we get n plus 1 times n factorial over n factorial times the absolute value of x, actually, right? See, because the x to the n plus 1 over x to the n cancels to give us x, just plain old x, right? Why can't I make that cancellation without apology? What am I assuming about x? It's not equal to 0, which means that cancellation, that algebra is valid. The n factorials cancel. And what do we, ooh, bad news, folks. Look at this. N plus 1 times the absolute value of x. What happens as n goes to infinity here? This goes to infinity, right? So what's the domain of this power series? Apparently, it does not include any non-zero x. The domain is the single point, 0. That's a kind of weird domain, isn't it? But that can happen. If the coefficients grow stupidly fast, like n factorial, then the only thing in the domain for the power series is the center. again, a power series has this form. The center is whatever appears here in the form. X naught is the center. Your question is good because it reminds me I should do something, which is show you some things that are not power series. Non-examples. How about this? F of x equals to x squared plus x minus 1 squared. Not a power series in its current form. Power series, when saying something's power series speaks to a specific form of the equation. The fact that you could rewrite it and make it into a power series does not make it a power series. I'm talking about the current form of the expression. So this is not a power series because if I asked you what the center was, you couldn't tell me. Is the center 0 or is the center 1? You can't have both. All right, this is not a power series. To make this into a power series, I could do and I guess to be fussy, I'd really like to, I mean, just for the sake of not being really annoying, let us agree that, I don't know, this is where it gets fussy. I'm inclined to say, okay, good enough. Goon, good enough. Right? I mean, the fussier part of me says, I want you to write the x squareds together. This actually matters later on when you're using theorems for power series to have collected all of the like powers together. There are things we say later that if you don't do that, you'll be wrong about what you say. So it's important before you apply a theorem for power series to collect all of the like powers. So like over here, this is definitely a power series. It's kind of stupid too, right? It's a polynomial. But this, not a power series. You mean to tell me you can have two things, one that's equal to the other and one be a power series and one not? Yes, I do. I do in fact mean that. That's also true over here. The left-hand side of this expression, right? The left-hand side of this expression is a power series. The right-hand side of this expression is not a power series. It is a rational function in x. These are different things, even though we have equality here for all x. Okay? So saying something's a power series is saying something about the explicit form of the expression for the formula. Another example would be something like f of x equals the sine of x plus the sine of 2x over 2 plus the sine of 3x over 3 plus dot, 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 dot. Yep. Sure, go for it.
Would the 2x squared minus 2x plus 1, would that be then considered a power series?
Yes, this is a power series.
So you're just changing the form to create it?
Yes, yes, yes. Yes, sir.
But it's not in that form, so how is it a power series?
What do you mean it's not in that form? Oh, so that's the other thing I was saying. To be really fussy, and you're being really fussy, and I like that. I like that a lot. So you're saying it's not in that form because I have not written 1 minus 2x plus 2x squared. Am I right? Right?
But it's a function. So are you just like, that's like a function, it's not a series yet. It's like,
Well, this is a series. It's just plus 0, plus 0, plus 0. So from this we can see C0 is 1, C1 is minus 2, C2 is 2, Cn is equal to 0 for n greater than or equal to 3. Great question. You just got to use your imagination to see what's not there. Lots and lots of zeros. So you were not fussing with me about the order of the terms. You were fussing with me that there's 3, not infinitely many, right?
yeah.
Good, good.
The power series doesn't have to be
a power series is a special kind of function. A power series can be a polynomial function, but it doesn't have to be a polynomial function. Like this, of course, is a polynomial function, right? Whereas example 1, is this a polynomial function? The answer is no on either side, right? This is also not a power series. This is what's called a trigonometric series because it's a sum of trigonometric functions. In fact, to be more specific, this is an example of a Fourier series. Fourier series are sums of trig functions, right? I'll talk about those at the very end of class, most likely. Not today. These are interesting for their own reasons. Power series, though, the reason they're called power series is they're a sum of power functions. What's a power function? F of x equals to x to the power n, right? That's a power function. So they're called power series because they're sums of power functions. Is this enough non-examples? Let me stop with my non-examples. All right, so we've seen an example where the domain was a finite interval, -1 to 1. We've seen an example where the domain was just the center, right? Let's look at a third example here. Example 3. F of x equal to a sum n equals 0 to infinity of x to the n over n factorial. Oh, why am I using this horrible thing? What's wrong with me? Why am I using this marker? It's garbage. Let's see here. So, let's see here. Let's identify the a sub n, fix x, right? Fix x in the reals. So what I'm trying to say is that really doesn't mean, conceptually it means I'm not thinking of x as a variable. Think about x as being a fixed thing. This is a somewhat stupid, I'm really making more of a conceptual point than a logical one there. So a sub n is equal to x to the n over n factorial. When you make a step like that, the question is, are you going to be able to hack what comes after it, right? Like, can you make statements that are true independent of your choice of x? It's because if you can't do that, then you're kind of stuck, right? But it turns out we're going to be able to do that, I think. Well, maybe I want x to be non-zero, right? Let's assume x is not 0. Can you guys tell me what happens? Oh, I guess I should write out the first few terms here, right? This is 1 plus x plus 1/2 x squared plus 1/6 x cubed plus 1/24 x to the 4th. Dot, 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 dot. All right. So, all right. I want to, 0 is in the domain, right? F of 0 is again, is f of 0 always 1? You start to get the impression that it's always 1, don't you? That's just a quirk of my first 3 examples. Sorry about that. But yeah, f of 0 equals to 1. 0 is in the domain of f, right? It's starting to seem like the center is always in the domain, isn't it? That is in fact true. If a power series centered at x0 will be in the domain. That is true. So let's look at the ratio test. As I have mentioned, this will reveal the interior for the domain of the power series, because wherever a power series is convergent, in the interior of that space, whatever that is, we actually have absolute convergence. All right? So here we go. Absolute value of a sub n plus 1 over a sub n, what do we got? We have the absolute value of x to the n plus 1 over n plus 1 factorial times n factorial over x to the n. What happens here? We get absolute value of x, right, times n factorial over n plus 1 times n factorial. The n factorials, they be canceling, and looks like we're going to get absolute value of x over n plus 1. That's my quote-unquote lambda. Which is a much better situation. Like the last time we had what? I erased it, but I'll write it back here again. We had absolute value of x times what? Times n plus 1. You notice the difference between example 2 and example 3? In example 2, we had multiplication by n plus 1. In example 3, we had division by n plus 1. But it's starting to seem like we always get an absolute value of x that factors out when we apply the ratio test, right? Provided we're not at the center for the series. What happens as n goes to infinity? This goes to, right? Wait a minute, but for what? What's the condition on x? There's only one condition, right? X is not equal to 0. Otherwise, no condition, right? So that says that this argument by the ratio test says that all non-zero x are in the domain of the power series. That's kind of nice. And 0 is also in the domain, right? So what's the domain? The domain of this power series is minus infinity to infinity. It's the whole real line. Yep. The center we choose by inspection of the given problem. So it's whatever you see in the original formula. If it's a power series, there has to be a center. We get it by looking at it. It's by inspection where the center is.
So how do we look at that last one?
Because I'm looking at a sum of powers of x, which is x minus 0 to the n. So it's x minus 0 squared, x minus 0 cubed. Yeah.
What does the center mean? Is it just like the center of like the power series? Is it like?
Well, its meaning is defined in the definition. The reason it's called the center is what I'm about to say. So, but I mean, like the terminology should start to be clear. The center is always in the domain of the power series. And in fact, if you look at it, we can define what's called the radius of convergence. All right, and so basically you can go from the center plus or minus the radius of convergence, and that gets you the interior, not including the endpoints, that gets you the interior of the domain. Let me write it down. Maybe that'll help. So this is a theorem. Given power series, sum n equals 0 to infinity of like Cn x minus x naught to the n, right? Then the domain of f of x, I'm calling this power series f of x, okay? The domain of f of x has one of the following forms. Step number 1, I'll start with the most boring possible case. The domain of f of x could just be equal to x naught. That's one possibility. It could just be the center. That was our example 2. The other possibility, it could be everything. All right? That's another possibility. The third possibility is actually a bunch of possibilities. The third possibility is that the domain of f of x is either, one of these 4 things. One of these 4 following things, all right? It's the open interval, x naught minus big R to x naught plus R, right? Here R greater than 0. There exists an R greater than 0 such that it's one of these things. It's the open interval from x naught minus R to x naught plus R. It's the closed interval from x naught minus R to x naught plus R. It is the half-open interval. Now, silly people will refer to the following as opposed or clopen. So let's see. A clopen set would be like this: x0 minus R, comma x0 plus R. You laugh, but I've seen it in serious math books. Clopen. Opposed. These are the possible domains for power series. In those last 4 cases, all right, the open interval of convergence, IOC, is x naught minus R, x naught plus R for all of these, for each one of these cases. The open interval of convergence in case 2 is the whole real line. The open interval of convergence, or the interior of the interval of convergence in case 1, I just wouldn't talk about. All right. So I just used this letter R. This R is called the what? This is called the radius of convergence. What's the radius of convergence in case 2? The radius of convergence, which is R, is infinity in this case. What's the radius of convergence, or ROC, in case 1? Right. Now I'm defining radius of convergence in this statement of the theorem, if that's okay with you guys. But the reason that radius of convergence is a reasonable concept is because this theorem is true. Why is this theorem true? What's the proof of the theorem? It's not actually that hard. Let me prove it. The proof is really what we've already done in the examples. I'll lay it out for you. Proof. Notice f of x naught equals to what? C naught, right? If you plug in x naught into the formula that's given, what remains? Just the constant term, right? The constant term happened to be 1 in my first 3 examples, which is why we had f of 0 as 1. 0 also happened to be the center of my first 3 examples. My apologies. So boring. But generally, the center is going to be in the domain because if you plug in the center, you get the 0 series for every n larger than or equal to 1, and the constant term just sits there, and there it is. So therefore, x naught is an element of the domain of f of x. Point number 1. Point number 2, let x be not equal to x naught, then a sub n equal to cn times x minus x naught to the n, right? Gives what? The absolute value of an plus 1 over an equal to what? This is a cheat. I'll let you guys see. You guys see if you can figure out why this is a cheat. Confession, I'm only giving you the proof for a special class of power series. The class of power series that my proof works for are power series in which every coefficient is non-zero. Because if that's not the case, applying the ratio test is ill-advised, right? But just stick with me for a second here. Suppose we're working with power series with non-zero coefficients, so that I can make this simple argument. What happens then as you look at the ratio test? Either the ratio of Cn plus 1 to Cn goes to 0 independent of x, right? In which case the radius of convergence is infinity. That was our example 3. Or what? Or this ratio, Cn plus 1 to Cn, goes to some positive number, right? And so if you look at the condition that this is, if you look at the condition that this is less than 1, that implies that, the absolute value of x is less than Cn over Cn plus 1. And you can identify, oh, I'm sorry. Good grief. That doesn't work out to x. Sorry, I'm hurrying too much. That works out to x minus x naught when you do it. So if that's less than 1, that implies that, I'm sorry, I shouldn't have done this. Oh well. That's less than that. And then you can identify that that is in fact the radius of convergence in this special context. Obviously, a different proof would need to be given in the case we had 0 coefficients, right? But this is in fact a general theorem of mathematics for for this course at least. The power series, the domain of a power series will fit into one of these cases. So as a student, you're trying to figure out the domain of a power series, your job is pretty simple. What do? First of all, identify, is this a power series, right? Because if it's not a power series, asking you what its interval of convergence and radius of convergence is doesn't necessarily make sense, right? But if it is a power series, then you use the ratio test, right? The ratio test will show you what the radius of convergence is. If the radius of convergence is infinity, you're done. The interval of convergence is the whole real line. If the radius of convergence is finite, all right, then it's one of these 4 cases, right? Now, depending on the context, you may or may not need may or may not already know that the endpoints are excluded or included. How do you figure out whether endpoints are included or excluded for a given example? Yeah, exactly. You just try them. You plug them in and see what happens. Or, as was the case in our first example, you make an educated observation, right? By the geometric series result, we knew that -1 and 1 were excluded in example 1. We didn't even need to check the endpoints here because we know we love geometric series, one of our best friends, right? But anyway, that's pretty much it. I'll do an example maybe or two tomorrow. But I want to get on to how to calculate with power series, which is really the more interesting part. So you can hit the record button. Thanks.